Good morning, everyone. So, thank you for having me for this presentation. So, right now I want to present my research with my college and my professor. And my name is Muhammad Abdullah. I'm from Tokyo Metropolitan University in Japan, and Shuhei Karashima from NTT Communication, and my professor is Mario Takao. So, before that, this is my title. It is a bag of tricks toward enhanced shuttlecock detection from badminton videos. So, this is a research about a sport analysis. As you can see, you can know Japan, Indonesia, and Thailand is very competitive in badminton, you know, right? So, this is a badminton videos of the maybe match between Japan with Korea. This is a technical analysis on badminton. Shuttlecock trajectory provides essential information to compute timings and other shot parameters. Therefore, shuttlecock trajectory information from badminton is very highly demanded. There is some work in the last year, there is 2020 by Sun et al. This is a paper from Taiwan. This is a TrackNet V2. It's proposed to detect the shuttlecock from badminton videos. And the architecture, they use a UNet-based encoder-decoder framework. This is called UNet because it's like a U shape. You can see that. This is like U. On the other hand, TrackNet V2 use a ReLU activation. ReLU is some activation in the neural network, which can cause issues with the dying ReLU issues. So when the ReLU is dying, the information of shuttlecock will be gone. There is a misdetection in the shuttlecock. And in the TrackNet, there are many batch normalization in the neural network, which can cause over normalization. So the location of the shuttlecock is some type of miss. And due to the depth of the network, TrackNet V2 might suffer a well-known called vanishing gradient call. I can go back to the unit. There are many layers. At the center, the layer is very small. So it will be called vanishing gradient call. In here. So this is a network structure of our proposed model. So this is our method. So I'm sorry, this is so small. So the first is input, and the last is the output. And I still use a UNet-based encoder. This is encoder, and this is encoder. This is, and this is. So let's jump to the inner part of our method. So this is the encoder, and this is the decoder. So this is our change for the proposed method. So before I make this network, the activation still use ReLU. Then I change to use LReLU. LReLU is leaky ReLU. A leaky ReLU is when the negative value of the shuttlecock is still be detected. So it is not literally, for example, when the shuttlecock is hit the before net, it will be white and white. So the program will be called, there is no shuttlecock detection. But when I add the leaky ReLU, there is a minus value of the shuttlecock. It will be called as there is a shuttlecock in there, like that. And after encoder, there is a decoder. I also change the ReLU to leaky ReLU. Then next is batch normalization. So I added a batch normalization because there are many batch normalization in the TrackNet V2. So I add in the last of the layer, and it will be tackle the over normalization problem, like that. And this is a big part of my method. you can see this is like a unit structure from the TrackNet V2, but I added this residual network. So when we training such a deeper network, it's getting harder and complicated because I tell it's about a finite gradient problem, right? So with this residual network, I can get the benefit of the residual after the layer. So even the detection is getting vanished or disappear in the center, it will be go back because I take the value before the layer. So it will be the shuttlecock is well detected. This is the formula of the residual network. So you can see this is the double X. So if I back in here, this is an X and this is an X2. So you can see this is the formula of the residual network. This is so simple. So just add the before value and the after value, we can get the Y value. Then after we complete all the method, we go to the experiment. Then we use some public data sets. This is some many badminton matches from BBF. There is many shuttlecock, badminton videos, and I use 3 samples for testing data. This is a frame that not training for the neural network. So this is the training details when we did the training. This is the same parameter for the TrackNet. So when we compare, it will be fair for the result. And this is the result for the loss. So the green is the baseline method. It's called the TrackNet V2. And after I added residual, leaky value, and the post-addition batch normalization, the loss is lower. It's better than the TrackNet V2. Then this is the overall experimental result. So this is a confusion matrix. There is a recall, F1, accuracy, and you can see there are improving of value of recall, F1, accuracy, and the other. So this is the qualitative data or the quantitative data. And this is so in the A, this is a TrackNet V2, and this is our method. Let's see in the first picture. So the red is ground truth. Ground truth is the real location of the shuttlecock. So you can see there is detection is not very good in here. Okay, there is a green, right? Yeah, but the shuttlecock is in here. So also in here, and this is our method, and this is a detection. So for the conclusion, as for a result of our research, we were able to develop 3 training traits that can enhance shuttlecock detection, and then our method improves precision, recall, F1, and accuracy from that value. And this was accomplished by residual network and chain activation value to leaky value, and then a modified batch normalization. And in the future, we will still develop for the shuttlecock detection for my research. And we want to use a transformer mechanism to improve precision of shuttlecock identification. As you know, transformer is the base of the ChatGPT. You know, ChatGPT is the base. The base is a transformer, and the transformer is the base of transformer is the attention network. That this is a paper from Google. So I want to improve this research to use the transformer. And this is a reference, so I want to thanks to the Dragon Institute because this is the very first research about shuttlecock badminton, and then some other research about residual learning, residual normalization, and we use PyTorch for the implementation. So thank you for listening my presentation. So is there any question? Thank you.
So any question, please?
You adjust the TechNet version 2, or you just imitate and add the layer that's similar to TechNet version 2 by yourself and add some linking, some additional features, additional layer in order to reduce the residual loss. For example, you have to write each layer by yourself, or you use some from the TechNet version 2 and maybe transfer learning, right? And add some layer. Or another question, compare your work with the YOLO with some version. What is the difference between tracking the shuttlecock using the YOLO and using your approach? And when you talk, maybe the tech version 2 is better than some machine learning like the LessNet or not?
Thank you for the question. That's a very good question. So I will go back to the network. So this is I can say this is the continuation of the Triangle T2 but in the other outro. So this is not a transfer learning, but I made this network from scratch. But I use same architecture, but I modify because there is some issues when I train. For example, when I try 30 epoch, this is a very long time running of the neural network. When I added more epoch, it will be the loss is very deep, right? So I looking for the program again and what can I improve to the value, the loss is not higher. So I get 3 tricks to training the Triangle T2. So it gets better for the loss. And also this is not a transfer learning. So for the comparing with the YOLO, I never tried with that, but I want to show you the video. Yeah. So you can see the shuttlecock is very, very small, and this is the video is not 4K or 8K like today. This is from a YouTube. So this is very small, and after I try with other detector, it's completely not detect. It's just only detect maybe the player. Also, the racket is not detected in here. So that's why I choose other method. That's called Triangle T2, and then I improve it. So it's detected very well until 88 precision. Thank you.
You move maybe the short part, the small rectangle by yourself, or when you what is the elaborate how can you move the rectangle and then put it in the neuron in your machine learning classifier, and talk a bit more about your feature and about all the training data that you use.
See, so thank you for the question. So there is a data set called shuttlecock public shuttlecock detection data set. So in here we can get the label of the shuttlecock and the frame too. So I didn't add some labeling, so I used a public shuttlecock detection. This is a public, so yeah, I didn't do labeling because I focused on the architecture. And for the future, I want to implement the transformer because I still confused about how to implement the transformer because the loss is still high when it's transformer. So I need to do some research about attention. Thank you so much.
So just one question, very short question. How fast is it? It can be real time or count from real time. Is this possible?
So this is
Offline.
This is offline.
So the computation time is quite long actually, right?
Yeah, for training.
Okay, thank you very much. Thank you very much. So give a big hand, please. The next paper is about a vision-based